In this work, we present a new system for automatic motion completion between temporally sparse keyframes. This is reminiscent of the job of in-betweening in classical animation pipelines, where principal keyframes are drawn first and then the motion linking them together. Animation authoring softwares allow interpolation through spline fitting, which cannot operate on gaps of more than a few frames and cannot produce whole cycles of motion. Our system, based on adversarial recurrent neural networks, is more robust to long gaps of motion. In this sequence, random keyframes from a continuous motion are shown with transparency. The generated motion from our system is shown with solid color. The lengths of the missing transitions range from 3 to 44 frames, despite the neural network being trained with a maximum transition length of 30 frames. We embed our trained model inside a custom motion builder plugin that allows easy use in a production environment. Here is a simple workflow example where walking motion is extended and modified by simply copying and dragging its last keyframe in time and space. The generation of the in-betweening takes less than 2 seconds. The gate can be adjusted by simply moving the target frame and clicking the Generate button again. Then, the animator extends further the sequence with some turning motion using the same keyframe by moving it and rotating it in the scene. The same iteration process is then done by editing the location of the target keyframes. Here we study a sequence of 3 motion segments created from only 2 keyframes, a crouching one and a running one, that we duplicate in time and space. Our model provides a realistic motion respecting those keyframes, yielding types of motions that are often used in video games. It is then trivial to cover a wide range of spatial variations by simply moving the keyframes in space. This allows to generate transitions covering many desired angles. By modifying instead the timing of the keyframes, one can easily obtain temporal variations of the same motion. However, without our time until arrival embeddings, there's too much ambiguity in the desired pace to reach the targets, and the motion quality drops. Our scheduled target noise allows for sampling different transitions for a fixed context by distorting the target-related embeddings of the model. The level of stochasticity can be controlled, and disabling it yields a deterministic network. Using noise concatenation for inducing stochasticity doesn't work, as the network learns to ignore those additional dimensions. Since the model learns from real human movements, it is limited by the realism of the conditions it is given. If we take the same 4 keyframes but mirror the second one, an uncommon gate must be performed to make the transition in time, and the model struggles. Sliding back the last 2 keyframes also yields unrealistic conditions not in a dataset, and the in-betweening quality suffers. Finally, asking for superhuman speed by removing the second keyframe and shortening the sequence also fails. Here are some additional results on more challenging transitions. Although the motion remains realistic, it is hard for the model to continue a perfect one-foot hop. This could potentially be alleviated by providing a longer context before the transition during training. Here, subtle movements are queried and keyframes are shown with spatial offsets for clarity. Other challenging movements include dancing motions, which are present in our dataset. Here is an example performance obtained when using the whole dataset, compared to when using a dataset where dance motions have been removed, and compared to when using a smaller dataset of dance sequences only. In all cases, it is hard for models to keep the hopping motion going, but combining specialized dance motion with much more generic data significantly helps. Finally, we present the LAFN1 motion dataset on which our model has been trained. It contains more than 4.5 hours of high-quality motion captured in a production-grade recording studio. Motions include different types of locomotion, sports, fighting, stumbling, dancing, getting up, and interaction movements from 5 subjects. We are also releasing accompanying code to recreate baseline results found in the paper on our newly defined in-betweening benchmark.